Let us start lecture 20 and the course is corrosion protection methods, and the broad topic will be materials aspect for corrosion protection. And today we would talk on the selection part. How would we go for a selection of material for a particular corrosion medium? So, when we talk about the selection of material, it depends on several other aspects like strength aspect, toughness aspect, ductility aspect, as well as whether it has sufficient hardness. If we consider only on the basis of corrosion, so then three factors should be kept in mind. So, this is selection of material only on the basis of corrosion. So, corrosion is the basis, fine. So, now when we talk about corrosion related selection of materials, three factors which are very important. One is corrosivity of the medium, fine. What do we understand by the corrosivity of medium? So, let us consider cooling water system. So, cooling water system can start with fresh water or even a potable water. Then we can have polluted fresh water. So, polluted fresh water means some sort of contaminations from copper ion. So, if there are copper ions present, or let us say ferric ion is present in the fresh water, a little amount, that can lead to a corrosion on the materials. Okay. So, if we consider these two cooling water, so that means fresh water as well as polluted fresh water. So, here we have copper ion, let us say, or Fe plus 3 ion, 3 plus. So, if we try to see the corrosion effect on aluminum, fine. So, this one can lead to a serious pitting on aluminum, okay. But this aluminum can be used for this application, this freshwater application quite nicely. So, that means on the same material, the corrosion effect exerted by these two medium is different. So, polluted freshwater has a higher degrading effect on aluminum than freshwater. So, I can say polluted freshwater has higher corrosivity, fine. So, this has higher corrosivity. Of course, fresh water would have lower corrosivity if we compare the corrosivity of these two medium on aluminum. So, that indicates the corrosivity of the medium. Then the second part is corrosion protection or corrosion resistance of the material, fine. Now, if we compare, let us say, polluted fresh water so the medium is same. So, that means corrosivity is fixed, and we see two material, one is steel or plain carbon steel, another one is copper nickel alloy. we call it KANPUR-NPTEL. So, that can have a 70% copper and 30% nickel, these are in weight percent level. So, that alloy can resist polluted fresh water better than the plain carbon steel. So, that means in the if the corrosivity is fixed, that the medium is fixed, then different material can have different corrosion resistance, and the corrosion resistance can be written the inverse of. So, this is corrosion resistance in the same medium can be actually inverse of corrosion rate. Okay. So, this equation, if you see, higher the corrosion rate, lower is the corrosion resistance. So, now we understand what is corrosion resistance of the material. That time we have to fix the corrosivity of the medium. Now, the third part, this is very important. Now, we know corrosivity, we know corrosion resistance. Now, the third factor which is to be fixed, that is acceptable limit for rate of attack. Okay. So, let us say I would allow that material in a particular corrosive solution. Okay. That means we are fixing the corrosivity. I will allow, let us say, 0.25 millimeter per year, that is the allowable corrosion rate or acceptable corrosion rate. If some material shows the corrosion rate more than that, so that material will not be suitable in that particular medium. So, that means that acceptable limit for rate of attack needs to be prefixed before we design or select a material in a corrosive solution. Fine. So, these three factors can have a relation. Okay. What is that relation? So, we can have a relation like we can put a corrosivity on y axis and then corrosion resistance on x axis. Fine. Now, in fact, when we talk about corrosion resistance in a particular medium, we can actually make them distributed in a decreasing order or increasing order, and we can assign some number. Even corrosivity is also a qualitative in sense. We can assign some number to this particular, to different electrolytes or corrosive materials, a medium. Now, for example, if we understand fresh water and polluted fresh water has got a higher attack ability on aluminum. So, that means we can actually, and fresh water has a limited attack ability on the aluminum. So, we can say that fresh water can be having some random number, let us say I assign some number, let us say 1. I can assign some number for the polluted fresh water as number 2. So, and it is also increasing order. So, that means I can put fresh water here indicating some corrosivity 1, and then polluted water I can say corrosivity number 2. So, like that way I can put all those corrosive solutions one above another. So, it is a kind of a qualitative assessment, how much is the degree of attack exerted by the corrosive medium on the material. And similarly, on the resistance part, I can also fix a particular medium and then see what is the rate of corrosion that would be exerted, that would be felt by the material. Fine. Now, in order to understand this, we have to also see what is the acceptable rate of attack. Okay. So, now whenever I talk about acceptable rate of attack or the failure rate, I can generate a kind of a graph like this. It is a kind of random graph depending on the analysis that is done in the lab scale, that what is the corrosivity of the medium as well as what is the corrosion resistance of different materials. and then we are actually putting those in a graph form. So, this is basically acceptable rate of attack, rate of failure or attack. Okay. Now, if I fix a particular corrosivity, fine. So, this is fixed, and I also have an idea for two materials at least, aluminum as well as copper nickel alloy. So, I have put those two examples, copper nickel alloy, for example, plain carbon steel and copper nickel alloy. I know that the plain carbon steel cannot withstand polluted fresh water, it can have aggressive attack. I have to use copper nickel alloy 70-30. So, then I can actually put them in this fashion. So, this copper nickel alloy can have position here, and let us say iron, this plain carbon steel can be put up here. So, that means I could see that the corrosion resistance of copper nickel is more than the plain carbon steel. Now, corresponding projection on the x axis, it shows that this projection, sorry, I made a mistake. Let us say copper nickel is here, fine, copper nickel is alloy is here. Now, when I put a polluted fresh water and then I can go to a point on the acceptable rate of failure, and I know that if this is the acceptable rate of failure, plain carbon steel cannot hold good because that rate is much higher than the plain carbon steel corrosion resistance. So, copper nickel alloy has a much lower corrosion rate, that means higher corrosion resistance in that particular corrosive solution, that is the polluted fresh water. So, and also we see that that particular projection on the x axis, that projection is left to the corrosion copper nickel alloy on the corrosion resistance axis. So, that means anything on the right side of it, this projection on x axis, we see the materials, whichever materials are coming, they are actually, so let us say this is copper nickel, this is stainless steel, like that way. So, they are coming on the right. So, we can say that those can be accepted. So, we can say accepted region, okay, any material falling on the right of this projection from the point of intersection between the corrosivity and the acceptable rate of failure attack. So, then on the left side of it, any material which are coming and sitting there, so they will not be able to withstand the corrosive ability of that particular medium, fine. So, that material should not be chosen there. So, this actually decides which material are actually coming up in a kind of a box where from I should select one of them, fine. So, that means all those materials on this are actually can be selected, okay, and left of it all those materials which are coming, let us say some of the materials they cannot be selected, let us say aluminum is here, aluminum is here. So, then aluminum can also not withstand this polluted freshwater system, fine. So, this gives me a kind of or gives us a kind of acceptable criteria. Criterion you can say, fine, on the basis of this hypothetical plot. So, this is basically a hypothetical plot. Now, once we know that there are several materials which are falling in that acceptable region for this particular corrosivity, which is polluted freshwater, now we have to decide few other things. What are those few other things? We have to see whether it is cost effective, fine. So, for example, instead of copper nickel, if I go and choose titanium, that would also hold good for this particular corrosive medium, but the cost escalation would be very, very high. So, we should choose something which has a lower cost for the application. So, this is cost effective. Second one is the availability. So, if some material, even if it shows a very good resistance, then we should see that that material should be available in that particular region of application, must be very easy. So, easy availability, the second criterion that should be considered for final choice of the material which is to be used in polluted freshwater. Then third one is, you can actually think about the processing. On as well as fabrication. Fourth one is ease of fabrication. Now, processing, let us understand what is the meaning of this processing. Let us say if I talk about copper nickel system, or let us say even Admiralty alloy, which is a low cost copper based alloys, like where we have, let us say in this particular case, here I can put one more alloy which is copper based alloy, copper zinc SN. So, it is 70%, 29% and 1%. So, this is called Admiralty alloy. This material can also withstand the corrosive nature of polluted freshwater. Now, we have two materials, one is copper nickel, one is copper zinc tin. Copper zinc tin would be much cheaper than copper nickel, because nickel is very costly. So, and at the same time copper zinc tin, the processing is not a problem. I think processing for copper nickel as well as copper zinc tin, both are almost on the same level, and fabrication part also, both can be fabricated quite nicely. Okay. So, now come to the cost part. So, copper zinc tin, if it qualifies for that particular corrosive medium, I should choose, because copper zinc tin alloy is low cost than KANPUR-NPTEL 70-30, right. So, this is about the cost part. Availability, both are available. Now, there could be a situation like the processing part, like let us say if I have titanium alloy and copper zinc tin, definitely the cost wise I should go for copper zinc tin, but at the same time, even if titanium shows a very good resistance, because titanium has the added quality, that is resistance against peating as well as crevice. The localized corrosion resistance is also very high for titanium, right. So, now we tend to use titanium. That means first of all cost part, and the second part is the availability is also an issue, because titanium alloys availability compared to copper based alloys will be an issue, because it will be not that easily available. Now, second part is the ease of processing. Titanium alloys, and if you compare the processing ability of titanium and copper, titanium processing takes a lot of money. Okay. That means if we try to get titanium first hand by reduction methods, okay, so there it will be costly. And ease of fabrication, definitely copper based alloys will be easy to fabricate, giving different forms than the titanium alloy. So, again I see that the fabrication as well as processing both would be a deciding factor in case both are cost effective and both are available. So, then we should consider all those two other factors, right. So, that means we could see that this particular hypothetical diagram, if we can generate for a set of corrosives which can be used for a particular application like cooling water application, right. So, then we can generate this graph and then finalize what material should be selected. So, let us give some more examples, like we have given a cooling water system. So, let us talk about cooling water, several other cooling water. So, let us say we left hand side we mention type of cooling water. And on the right side let us put materials which can be used. Okay. So, we can have fresh water, that time plain carbon steel. Aluminium, you can talk about copper, that can also work. Now, when we talk about polluted fresh water, there I cannot use plain carbon steel or aluminium, I can use a copper based alloy like Admiralty. Now, we can see that the corrosivity is increasing. At the same time, corrosion resistance is also increasing in this way. Okay. Now, we can have cooling water like brackish water. Or we can have sea water, but the condition is low velocity. Okay. So, now brackish water is nothing but the water from river meeting the sea. So, that particular zone will have little less salinity than the sea water. So, that water is termed as brackish water. So, there we should use costlier material with a higher corrosion resistance. There we can use cupro-nickel 70-30 or 90-10 nickel. So, these alloys can withstand the corrosion ability of those medium, and in fact, you could see that the corrosion resistance is further improving in this particular direction, downward direction, as well as the corrosivity is further increasing as we go down. So, that means if we fix a particular acceptable limit for attack, then we can actually decide which are falling on the right side of that acceptable limit or left side of that acceptable limit. The right side, as per that corrosivity corrosion resistance plot, on the right side of it, after having the projection on the x axis, which is the corrosion resistance, we can use those materials which are actually on the right side. So, that means now we have to choose which one to finally select. It depends on 4 other factors like cost, availability, ease of processing, ease of fabrication. Okay. Now, we can go to a much serious corrosive solution, much higher corrosivity like pure and polluted seawater. Now, it can be of high velocity. When it is high velocity, generally the pitting ability is not that high, because we know that with increasing in velocity, the pitting tendency reduces. So, high velocity seawater, even if it is polluted seawater, still we can think of using austenitic stainless steel, or we can use austenitic stainless steel, but if it is 304, there could be a possibility of peat formation. So, that is what we have to have molybdenum in it, which can actually prevent peating. So, we can use 316 type, where we have molybdenum. We can use ferritic, stainless steel with extra chromium as well as molybdenum, fine. So, these two things we can actually prevent the peating ability in polluted seawater, but high velocity, remember. So, the high velocity actually reduces the peating ability, but still if we want to avoid further peating, we can use molybdenum added steels. We can also use titanium, fine. Now, so that means you could see this particular range, still they are having much higher corrosion resistance, and remember the corrosion resistance is actually increasing as we go down in this particular table. So, further the corrosion resistance increases and corrosivity of course increases further as we go down. The final one, we can have polluted seawater with low velocity or even stagnant. So, that time we can actually cannot use even 316, we can use titanium based alloy or much high content, high molybdenum and chromium content ferritic stainless steel. Okay. We can also go for nickel based alloys with much higher molybdenum content. So, nickel based alloy. So, like Hastelloy or Inconel, which has much higher molybdenum content, more than 10%. So, that gives very good corrosion resistance, even very high corrosion resistance against peating or crevice. So, these alloys again the corrosion resistance further increases, and as you see that if we want to use these material, this the last cadre which is having the maximum corrosion resistance, for the first cadre of solution with the lowest corrosivity, it does not justify the use because the cost would go up, fabrication would be much high. So, we should go for a low cost material as well as easy available material. Now, this particular table again can be put up on this corrosivity as well as corrosion resistance plot. So, now let us see how would we take it up. Again, as we see that from fresh water to polluted seawater, high velocity, low velocity, I can actually mark them as, I just give some number, random number 10, 20, 30, 40, 50, and the corrosion resistance I can just mark them as some random number. I am just selecting some random number. Let us say this cadre I can put the number like, even I can put it as 2. Higher the number, higher is the corrosion resistance. I can put it as 10, I can put it as 30, set of materials I can put it as let us say 50, and the last one I can put it as 80. Okay. So, this is a random number I have assigned, that means higher the number, higher is the corrosion resistance, as well as on the left side, higher the number, higher is the corrosivity. So, I can put them like this with increasing number 10, 20, 30, 40, 50, this is corrosivity. So, I can put it as assigned corrosivity and this is assigned corrosion resistance. So, I am talking about these numbers. So, then I can put it like this is I can say first number we have put 2, then the second number I have put 10. If we see those numbers 10, 30, so the next number is 30, the next number is 50 and the final number is 80. So, these are corrosion resistance. Fine. Now, on the basis of just acceptable corrosion rate or failure, I have considered some number, some random number. I put let us say 0.25 millimeter per year. So, this is my corrosion rate in a particular medium. So, in different medium I can have a different corrosion rate acceptable limit. So, this corrosion rate limit can increase like this acceptable plot. I can have a plot like this, okay, like this. So, let us say I go like this, let us say I go 40, this is the acceptable limit. Acceptable failure plot, failure rate. Okay. Now, correspondingly, if we just project it on the x axis, on the corrosion resistance axis, I could see the right side of all those alloys, the 50 as well as for 80. So, that means if something is applicable for pure and polluted seawater with high velocity, where the pitting ability is less compared to the low velocity or stagnant case. So, I can use stainless steel 316 type or ferritic stainless steel, chromium, molybdenum or titanium. But when we go for polluted seawater, we can use little costlier titanium alloy as well as a higher content of chromium and manganese, chromium and molybdenum to have a better pitting resistance, or nickel based alloys. So, now all those material sets falling in this category, they can be selected for application in a medium with corrosivity 40, and that medium is nothing but pure or polluted seawater with high velocity. Fine. So, you can see a kind of relation between corrosivity and corrosion resistance with a fixed acceptable failure rate in different medium. Fine. So, that is the relation between all those materials listed on the right side of the table and all those solutions with the different corrosivity on the left side of the table. See, now we have understood the requirements, the basic requirements for selection. We will continue on the selection part. We know that there are several forms of corrosion, and broadly they are classified into two groups. One is localized, or a very like pitting or crevice, those are kind of a localized attack, or intergranular corrosion, and there could be one more mode which is uniform or general corrosion. So, these are two broad categories, and we will try to see that what could be the criteria for selection of material in those two broad segments of corrosion forms, if the material is experiencing those corrosion forms. So, till then let me end our discussion on the selection at this moment. We will continue in next lecture. Thank you.